Okay. So, we're on the solutions worksheet that we're going to use as kind of a lecture guide for the second day of Module 11 for chemistry, obviously. The last video covered the first 9 questions, so we're on question 10. It says to calculate the molar mass of KCl. If you haven't actually done all these questions, please stop the video and do them. But you should find the molar mass of KCl to be 74.6 grams of KCl per mole. Okay. The molar mass 74.6 grams per mole. And it says what is I for KCl? Can be dissolved in 100 grams of water. That 100 should be 3 significant figures, not 1. There should be a decimal point after it. To yield a saturated solution. What is the molality of that saturated solution of a room temperature KCl solution? So hopefully you've done it. Remember that when you're doing molality, you're doing moles of solute, which is KCl, over kilograms of solvent, which is water. So when you're trying to find the molality of that solution, you want to do moles of solute over kilograms of solvent. So it tells you that about 35 grams can dissolve. I can't put the KCl, it just won't fit on the board if I do. So you're going to use your molar mass to cancel the grams and get moles. So 1 mole of KCl is 74.6 grams. So that'll cancel my grams and leave me with moles. But molality is moles of solute over kilograms of solvent. So we need to divide by kilograms of solvent. Little m of KCl, 4.69 molal of KCl. And I've got 3 significant figures everywhere. Your worksheet has that mistake for the 100 grams not being 3, but if you keep 3, you should get 4.69 molal KCl. And then it wants you to calculate the freezing point for this solution. So I'm going to leave the answer there at the bottom and erase enough stuff that I can fit some more work on the board. Times the freezing constant of water, which is always 1.86 degrees Celsius per molal, which is fun units, but you know, times the molality, which we calculated to be 4.69 molal KCl. So if I type in my calculator 2 times 1.86 times 4.69, the 9 I promise, then what I actually get is delta T equals negative 17.4. And molal cancels here, so I just end up with a unit of degrees Celsius, which is great for temperature. But that is not your final answer, and you must go one more step. So the change in the freezing point is going to be 17.4 degrees Celsius. Since water's freezing point is always 0, you have to do that extra step. delta T, because if you have a different solvent, you're going to have a different freezing point that starts here. So you've got to be really careful. People mess that up on the final a lot because I don't give you water as a solvent. I just give you a different KF for a new solvent. So pay attention. Even if Dr. Wile's not that mean, I am. So we found the freezing point of that solution. So now if we move on, you know that solubility of a solid in a liquid increases as temperature increases. So if we increase from room temperature up to 90 degrees Celsius, closer to the boiling point of water, we can dissolve more KCl. And in fact, about 52 grams of KCl can be dissolved it tells us that we'll have, start over here, 52, and it doesn't even say 52. But we have to divide by kilograms of solvent, which is water, and it tells us we have 100 grams, so that's 0.1 kilograms of solvent. So I type that into my calculator, and I find that this molality is 7.02 significant figures because that limits us. And I'm, again, assuming 100 grams is 3, not 1, because that would be silly of me. I can measure better than that. Molal KCl. So at 90 degrees, a saturated KCl solution is actually 7 molal instead of the 4.69 molal it is at room temperature. You can dissolve much more KCl in hot water than cold. Problem 14 says we have 30 grams of KCl. If you buy it from Home Science Tools, you only get 30 grams. You don't get 52 grams. And, you know, I'm not going to buy 2, so we're just going with the 30 grams that we have, except it's a snow day, so I'm not doing it. But we'll talk through it. You guys can picture in your mind here. We've got our 30-gram bottle of KCl. How much 90-degree water should we use to make that solution 7.0 molal? Okay, so remember that 7.0 molal really means 7.0 moles of KCl how to make the solution. How much water do I need if I only have 30 grams? .0 moles of KCl. Just flipping the molality over. You can always and then I know I can cancel grams. Oh goodness, my thing has turned off. I can cancel grams by remembering that I'm going to use 30.0 grams because that's what comes in my little jar of KCl when I buy it. So that'll cancel grams here. So if I type this in, 30 divided by 74.6 divided by 7, then I get this, 0.74 0.0574. 0.574. And what's my unit left? The only thing left is kilograms of water. So 0.0574 kilograms of water, which doesn't fit at all. So what does that actually mean? Well, that actually means, if I convert from kilograms to grams, 57.4 grams of water. Well, I could put that on a scale and measure out 57.4 grams of water, but that would be silly because we know the density of water is 1 gram per milliliter, so I can just use a graduated cylinder to measure 57.4 milliliters of water. So the overall answer for number 14 is going to be, take a graduated cylinder, measure 57.4 milliliters of water, and then just add the whole 30.0 grams of KCl to it. And that's going to give you this 7 mol solution with what you actually have purchased. So, when you buy some random amount of chemical or you only have this little bit left, you just have to take what you have and do the math to figure out how to make the solution that you need. So if I then get that, 57.4 milliliters of water up to 90 degrees, it will actually dissolve all of that 30 grams of KCl. If I use room temperature water, of course, it's not going to dissolve it. So right now, if we were in class, what I'd do is I would heat up some water, get it up to a boil, so that by the time I measure 57.4 milliliters of it, it will probably be about 90 degrees. And then once I have 57.4 milliliters of it, I'll just add that KCl, dissolve it. Then it's a saturated solution at 90 degrees Celsius. So then, if we move on to problem 15, it says this. What do you think will happen if we cool this hot saturated solution of KCl? So what I would do then is just take a little bit of that solution and put it in a test tube. It's a good saturated solution, pour it into a test tube and plunge it into some ice water. So when I cool off the test tube, obviously I cool off the solution, can all that KCl stay dissolved in cold water that is dissolved in hot water? And of course we know the answer is no. So what will you see? So think that through. What are you going to see as that solution cools? So just like the hot tub problem that Dr. Weil talked about, why your hot tub gets cloudy when it cools off, at a lower temperature, not all that solute will dissolve, so it will precipitate out. So number 15, the solid KCl will come out of solution. If I could do it in front of you, it doesn't really show up on video, but if I had done it, I took the hot saturated KCl, got it cold, some of the KCl would just come out of solution and form a white solid right in the bottom of that test tube because it couldn't all stay dissolved at the lower temperature. Number 16 says, what is an insoluble solid that comes out of solution called? And that's called a precipitate. Of course, we've talked about that. So then, just to emphasize the difference between molarity and molality, I ask you how to make a 7.0 molar solution of KCl with the 30 grams of KCl. So if I boiled away the water, reclaimed my 30 grams of KCl, and wanted to make a 7 molar solution instead of a 7 molal solution, it would be similar to the first video for today, where I made the saltwater solution, a molar solution, and a molal solution. How would you make a 7 molar solution? Well, 7 molar means 7.0 moles of KCl per 1 liter of solution, of total solution, right? Totally different than molality, even though it seems similar. This is molarity, so it's 7 moles of KCl per 1 liter of solution. But we need to find out how much total solution to make for that 30 grams that we have, right? So once again, we're going to invert our molarity in this case. So we're going to say, if I make 1 liter solution, I need to use 7.0 moles of KCl. Well, I don't have 7 moles of KCl, I only have 30 grams. So I can't make a whole liter of solution. How much can I make? So I'll use the molar mass again to cancel moles and get grams. So 1 mole of KCl has a mass of 74.6 grams. Cancel my moles, now I've got grams. Of course, we know we only have that jar of 30 grams of KCl. That'll cancel my grams, and I get the exact same answer, 0.0574. And my unit here is liters of total solution. Live this on film. But 574. So 0.0574 liters is really 57.4 milliliters of total solution. But you make the molar solution in a completely different way than you make the molal solution. You would first measure out that 30 grams of KCl and then add water. You'd have to use a graduated cylinder instead of a volumetric in this case because they don't make a 57.4 milliliter volumetric flask. But if I want to use my whole 30 grams of KCl, then I would use a graduated cylinder, put in the 30 grams, and then dilute it to 57.4 milliliters of total solution. Okay, so different way of making the solution. For molal, you measure the water up to 57.4 milliliters, and then you add the KCl. For molar, you add the KCl and then dilute with water up to 57.4 milliliters. So you watch me make a salt solution of both of those, so hopefully it's clearing up the difference between molar and molal. In 18, it says, which solution would have a greater volume, the 7 molar or the 7 molal KCl, if we made them with 30 grams of KCl. So we're comparing the answer to number 17 here with the answer to number 14 over here. So which one have a greater volume? If I added the KCl and diluted up to 57.4 mils, or for the molal solution, if I got 57.4 mils of water and then added the KCl. Well, clearly you can see that the molal solution will have a greater volume because I get all that water and then add more stuff. For the molar solution, add the stuff and then dilute up so that I only have 57.4 milliliters. So think that through. The molal solution is going to have the greater volume. Number 14 will have a greater volume than number 17, in other words. So this isn't on your paper, but which one will be more concentrated? And that, of course, would be the molar solution, because you have less water for that 30 grams of KCl in this molar solution. So this one is going to be more concentrated. The other one's going to have a greater volume. Same amount of KCl in both solutions. So hopefully you're thinking clearly now about molarity and molality. And now we're supposed to move on to number 19. Now this is something you guys have seen me do in class before, so you're not missing too much. Lye, which is sodium hydroxide, NaOH, number 19, is dissolved in water. What do you observe about the temperature? Do any of you remember? I've passed around the thing, and you can feel that the dissolving causes heat to be given off. It gets hot when you touch it. So you observe the temperature going up, it gets hot. And then number 20 says, what is I for NaOH? So if you think NaOH, first you want to think, is it ionic or covalent? Well, we know that's a polyatomic ion, OH. So it's going to break into ions because it's ionic. When it dissolves, it will be an Na plus and an OH minus. So it splits into 2 ions, so I is 2. 21 asks you, is dissolving a chemical reaction? So hopefully you've filled this out. And in fact, no, dissolving is a physical process, a physical change. It can be easily reversed. It's not a chemical reaction. So one of the indicators that we've talked about of chemical reactions is giving off heat. But in this case, dissolving can actually have a heat change, even though it's not a chemical reaction. So that's something to make sure we go over. Number 22 says, does the solid solute lye, you've seen me use lye lots of times in class, become a liquid when it dissolves? So is dissolving changing from a solid to a liquid? And that's a no. When you dissolve something, it's still solid ions suspended in the solvent. It hasn't become a liquid. For that melting process to happen, ionic compounds have to reach very high temperatures, maybe like 500, 600, 700 degrees to melt lye, to change it from a solid to a liquid. That hasn't happened, even though it got hot. It didn't get that hot. So dissolving is not melting. It's not becoming a liquid. It's still a solid. It's just being held in solution by the electrostatic forces between the polar water and the charge of the ions here. And we talked about that last week and lots of other times, I think. Let's see. Number 23 says, when a process, which could be dissolving or a chemical reaction, gives off heat, what is that called? So when a process gives off heat, it's an exothermic process. Exothermic. Number 24, barium hydroxide, which is a solid, a white powdery stuff, is mixed with ammonium nitrate, which is also a white powdery solid. One's kind of balls and one's kind of flaky. So they look a little different, and you can tell. And I'll do this in front of you guys next time we meet, or maybe the time after, depending. So I'm going to mix two white solid things together, and you'll observe them. And eventually, I'll just have to tell you 24 since you're not in class and you can't see it, but they're going to become like a slushy, like a liquid slushy, like a icy that you buy at Target or something. And they get really, really, really cold when you mix them together. So then at number 25 asks you, what is I for barium hydroxide? If you look at your periodic table, barium is a 2+, hydroxide is a 1-. It also asks you ammonium nitrate, so ammonium is a 1+, and nitrate is a 1-. So if we form barium hydroxide, then we're going to switch the charges, and we're going to get this. I for barium hydroxide, you'd form 1 barium and 2 hydroxide ions for every 1 particle of it that dissolves. So I is going to be 3. 1 barium, 2 hydroxides for a total of 3. I for ammonium nitrate. So ammonium nitrate, the formula for that would be NH4NO3. So when it dissolves, it'll form 1 ammonium ion, 1 nitrate ion, so I will be 2. So I for barium hydroxide is 3, I for ammonium nitrate is 2. Number 26 says, write the balanced chemical equation for this reaction. It's a double replacement. You guys had lots of practice with double replacement reactions last time we met. I think more than you probably wanted. So you just know, switch the cations with the other guy's anion. So you've got barium, it'll get the nitrate. Barium's a 2 charge, nitrate's a 1, so we'll get BaNO3, and then ammonium hydroxide, which would be NH4, and that's a 1, hydroxide's a 1, so OH. And then you have to balance the equation, because obviously it's not balanced. So we've got 2 NO3s, we need 2 over here. Here we've got 2 hydroxides, so we need 2 over here. So 2 ammonium, 2 ammonium, 1 barium, 1 barium, 2 hydroxide, 2 hydroxide, 2 nitrate, 2 nitrate. So now we're good. Yes, good. Okay, so 1 barium hydroxide plus 2 ammonium nitrates gives you 1 barium nitrate plus 2 ammonium hydroxides, and that's your balanced equation for that. Number 27 says, when a process absorbs heat, and in fact that's what you'll see, when I do this in class, that thing will get cold. That means just like an exothermic, when it's giving off heat, it feels hot. When something is endothermic, which is the answer to 27, it feels cold. It's actually taking in heat. So endothermic things feel cold because they're taking in heat. Exothermic things feel hot because they're giving off heat to their surroundings. And that's something you really need to get in your head before Module 13, because having that really straight will help you immensely. Number 28 says, would the products of an endothermic reaction, taking in heat, feeling cold, have a higher or lower energy than the reactants? Okay, so you mix these two things together, they react and form these two things, and they give off, or they take in heat, they feel cold. So if you take in heat here and they feel cold, it's literally going to a higher energy state. These guys are taking in energy. They have more energy than they did here because they're absorbing energy from their surroundings. That's why they feel cold. So number 28 is higher. The products here will have a higher energy than the reactants. And you say, well, you told us matter is lazy. Why does that happen? Module 13. But anyhow, I'm going to stop the video here, and then I'll go over review questions and practice problems on the next.
What are you doing?
I have no idea, Jojo. I have to stop the video and figure out how not to mess it up.
Are you done?